All right, so in the last video, we looked at how to do error handling in Odin, and we touched briefly on allocator errors, right? So we saw here that concatenate returns an allocator error, possibly, right? That means allocation can fail. And related to this is the concept of passing allocators to things, right? So this allocator here, this allocator error here rather, can happen much more likely with certain allocators than others, right? So if I were to look at this type signature here, we can see that in the type signature we have first a slice of strings, right? And that's, yeah, okay. Then we have this interesting syntax where we have allocator, right? Assignment context.allocator. So in this video, we're going to take a look at what the context is, what it contains, and kind of why these things are there, how we use it, how we can use it. There are several ways, and how it impacts our code. So let's look first here and see that this, if we go to the context, we can actually see that this is a normal struct, right? And importantly, this context in Odin is going to be implicitly passed to every function in scope. So when you call a function, implicitly the current context you have will also be passed to that function call. This is implicit. They call this the Odin calling convention, right? So it's built into how Odin does things, right? You can also use, you can remove the context from a call if you, for example, you don't want it there because it costs basically something to pass this and so on. That's also completely valid. But by default, when you call a function in Odin, from Odin, etc., you're gonna have a context, right? And so this context here contains an allocator, a temp allocator, and a logger. These are the three most important things to me. We also have a user pointer here where you can store a pointer to some data that you know that you want in some scope, and so on. You have a user index, this assertion failure proc, and so on. But the most important things are allocator, temp allocator, and logger, right? So in this, when we use this, right, we saw that one of the common usages here is allocator is equal to context allocator, like this. This now makes it so that read configuration optionally takes an allocator. Right? So if I go to my sandbox file here, we could pass an allocator here, right? What does that mean though? Right? If I run this code, this is how we would see it normally. We're going to see this. And here we just have to make a slight modification because I do want to see our concatenation here. So we're going to say, hey, return the parsed config here. And right, it seems like we have an error, and that's of course because we are checking if the file exists. We have error handling for that. And here, important reminder, if we have an error, if is not nil, fmt panic f, error reading configuration file, like this. So now we can see we don't have that error anymore, but if we did actually have this error, we would see this error reading configuration file, file read failed, file name ols2json, so on. Let's do that because it's nicer. And here we'll see that we have this prefix being added. And I'm going to, for lack of just imagination, paste this several times like this. Don't worry too much about that. This will just make it easier to surface certain behaviors. Now we can see that we have prefix there, a lot of it. So let's also say that we don't want ols.json. Let's make a new file called file1.txt. I'm going to say file1.txt here. And this file doesn't contain anything. This file doesn't contain anything, so because you can see here that we are allocating when we are reading that file, and I want to make this now I want to make this instructive and clear, and we're going to try to do it this way. So let's close that for now. Now this concatenate call here takes an allocator. Right? We saw this before. Second argument is an optional allocator. So what does that actually mean if we want to configure our program? We want to do certain things certain ways, guarantee certain things, and so on. I'm going to open a new tab here that we can switch to. There you go. Now, how do we deal with custom allocators and so on? One very common solution to this, or one common thing to use, is what's known as an arena allocator. So we're going to import some modules here, mem and mem virtual, and then we're going to say an arena. We have an arena, which is a virtual arena like this. We are going to say virtual arena init buffer, and this function here takes an arena to fill in, to initialize, and a buffer. So we're going to say arena, and then we're going to say, let's say arena buffer is, let's just say now, let's say 64 U8, not U8 bytes actually. Just let's say it's 16. We have 16 bytes for this, right? And here we're going to pass arena buffer. Importantly, this is a slice of bytes, and this is an array of bytes. The difference between these is one of them is the length is known at compile time. That's an array. This is an array, the arena buffer here. And if we want to actually make a slice out of an array, we actually have to use slicing syntax here. So slicing syntax is based on start and end, like this. If you omit both of these, you actually just say, give me a slice to the whole thing. Importantly, this is not a copy at all. A slice is just a pointer into something, right? Pointer into something like an array or whatever, in reality, right? So we're getting a pointer into this buffer here. And so if I do this, we save here, you can see here this requires that its results must be handled. So we can say, hey, arena init error is this. If arena init error is not nil, we want to do something. So we can say this, for example. Now we can switch here, Odin run sandbox. We're going to see we couldn't initialize the arena. That is actually because this here, this memory, is not large enough for initializing the arena itself. It has some amount of bookkeeping that it needs to be doing on its own, right? So we could, for example, say 64 here, and now we can see, okay, the program runs, right? And we could now try to find sort of the middle ground here. Okay, 48 works. Let's go to 40. 40 works. 38. Okay, so at 40, it seems like we're good. Right? So we have now, we've found exactly the limit. Well, not necessarily exactly, it could be 39 actually works, but we're going to leave it there, right? But what we've done here is we've put an upper limit on this, right? And we're allocating this memory on the stack, right? The array goes on the stack here. It is not dynamically allocated at all, this memory, in fact. But we're using this in our program as if it was. So we are initializing this arena here. We saw now that we are passing that, right? So we're passing this, but what if we want to use this arena allocator, right, in our program, right? So importantly, when I have this arena here, this is a virtual.arena. But we can see here that read configuration takes, oh, we can't actually see this necessarily, but it takes an allocator. An arena is not an allocator. But what we can do is we can create an arena allocator by saying virtual arena allocator and then arena, like this. And now on this line here, we will see that we have an allocator. So now we can pass this allocator here to our function, arena allocator, like this. And so now what should happen when we run this program? Well, it runs out of memory, right? Because we found the limit at which the bookkeeping for this arena actually, it could barely get going. And then in this file, right, we're using, of course, memory, right? We're allocating from this, right? And this gives us an immense amount of control. We've now set up a system here where, well, we could modify this number as we wanted, like to say, I don't want the program to be using more than this, right? If we're making a very small utility and we really, I mean, we know that what we're doing should fit in some amount of memory, for example. Importantly, these are bytes, right? So we could consider this just sort of, this is the bucket you can only get from this bucket and that's it. So we could, for example, say, you know, 4096. You get 4 kilobytes, right? We could say 8 times this, because I genuinely actually don't remember how much that would be. But you can use calculations here. This is done at compile time. So, or we could say, well, you get 256 kilobytes, right? And now we should, of course, see that our program runs fine. We're not using nearly 256 kilobytes. And this fits on the stack as well. And so this is an interesting kind of feature, right? We now get complete control over what happens in our program. We can say, you know, here's where your memory comes from. A different function could get memory from a different allocator, right? We can have allocators with completely different behavior, right? The arena is an interesting thing, right? Because it is very versatile and it's incredibly easy to use. If I wanted to, I had some complex program here and I wanted to say, you know, when we're done with this arena, I really want to free the memory, right? And of course, freeing memory is kind of where things get complicated. But with arena allocators, we can actually just say defer virtual arena destroy. And then we pass our arena. And at the end of this scope, what the defer keyword is going to do is it's going to run whatever is on the right side. And this will free all of our memory, right? And that's an incredibly interesting idea, right? This, you can see here also a buffer-based arena does not delete the provided byte buffer. That's of course because this byte buffer is on the stack. Stack memory gets thrown away at the end of scope regardless. So if we're using an actual buffer arena, we really don't need this defer virtual arena destroy, but it is still nice to have. And of course, buffer arenas, you have to be careful here because this is on the stack, so it will not outlive this scope. But yeah, so this gives us a lot of control, right? There's also a slightly different way to do this, and I'm going to just demonstrate that as well. This is a great way to use allocators. We could also, instead of passing the allocator here, we do know that this default value is going to be context.allocator. If you have a lot of these, or you just want kind of, you don't want to pass it around too much, you can just say context.allocator equals arena allocator. This will do the same thing, right? So if I were to now go down to our painfully small 40 bytes, we should see that it fails. That's because we are using this allocator. It has been set as the context allocator. And because the context is being passed to all of our sub calls here, we will be using this arena allocator for those calls, right? And this also stretches beyond here, right? When we go into this read configuration function, we would see also that this here, of course, uses context.allocator as the default value. So even if we remove this argument here, we would be using that one, right? So I can remove this from both of these, and it would still do the same thing, right? So if we do run this now, opa, I exited, that was a mistake, of course. There you go. We're still running out of memory, right? But I would argue it is nice to pass your allocators, not implicitly, but rather explicitly. It makes for a lot nicer code. And in your plumbing code, so not necessarily in your main application code or whatever, in your plumbing code, I would certainly say, make it configurable, make it a parameter, set it to be default context.allocator, and that's it. So there's one other thing. The temp allocator, by the way, is the same thing, except it applies to temporary allocation and so on. And temporary allocation is something we can kind of get into a bit later. This is the most important part of allocators in context. But there's one other aspect of context that I do want to get into here very briefly, and that is loggers. And as opposed to the allocator version, I do not tend to use these explicitly. So let's show what that means. When I want to log stuff in Odin, right? Let's say, for example, here that we want to log the parsed configuration. We're going to have a debug F here. Parsed configuration is this, and parsed like this, for example. We can go up here now and say core log. This is all built into Odin, of course. Now, when I run this, we're going to notice nothing. Well, of course, we have a memory error, an allocation error. Let's extend this to 128. Does that work? Yes, it does. So 128 works. And now, importantly, we didn't see anything being logged, though, right? That is actually, despite our log call here, right? We, in fact, do not have a logger in our context. By default, there is no logger in the context. So what we can do here is we can say context logger equals, and we're going to have log up here, log.create console logger, right? The console logger takes a few arguments, the lowest debug level you have, some logger opts, and then ident. And so these are not necessarily super important. We're not going to take a look at them necessarily now. Rest assured, they are actually useful. But we're just going to create a logger. We're going to save that file and run. And now we will see that, debug. We have debug here. And this is great actually for printf debugging, I would say. There you go. So this is really good for printf debugging. It allows you actually to very nicely deal with logging, because the context is passed to everything, right? And for logging, we don't actually want to pass it around that much, right? It actually obfuscates more than it helps. It tends to. Logging is one of those things that can show up anywhere, anytime, and so on. And it doesn't hold the same performance problems as an allocation does. Allocators, we do want to be specific because they do actually slow things down potentially and so on. And we want to control it very specifically. So taking that as a parameter is generally advisable. But with logging, I tend to at least say, I have a logger here. I set it to something, and then we kind of run the main program, right? And for different threads, you might have different loggers you set, and so on and so forth. Importantly, create console logger is kind of the one that I go by just for pretty much everything initially, right? But importantly, the logger is really just a thing. It's a structure that you can actually implement, right? So we can see here what a logger is, right? Runtime.logger. it has a logger proc. It has some data inside of it, a logger level, and some options, right? And you can build your own. There are utilities for building your own. So if we see here, for example, create multi-logger, right? Here you can pass multiple loggers, right? So for example, if I did this, we would actually see here I actually need a handle, right? So log file handle OS, let's say log file handle, log file open error, OS open, and I don't have OS. This OS open hello.txt, log.txt rather, and blah blah blah. Let's see, is this gonna be fine? And it is, right? So here we have a multi-logger. It will log to our console and it will log to a file, right? And here we could, for example, actually, yeah, this is read only by default, and that's not really actually what we want. We want OS, right. Let's say this one, actually, I don't know. Let's try running this and see what happens. Run sandbox, debug. Let's cat log.txt. Log.txt doesn't exist. We didn't check that error, so probably it just sort of skipped over the fact that that was an error. Now we can actually see, oh, we did not get double output, right? And what do we have in log.txt? Well, we have our debug message, right? And so creating this multi-logger here is fairly straightforward. And if you have your own logger, it might be, for example, AWS. You might be logging to, what is it called? Cloud something or other. Yeah, I don't remember what it's called. But you might be logging to AWS. You might have some other logging facility that you have written a logger for. And the logger proc in question is fairly straightforward. If we look at logger here and we go to runtime logger, we go to logger proc. Logger proc is this one. If you implement this, you can basically create a logger out of this, right? This is all just data. Feel free to implement it, right? Very straightforward. And so yeah, that's the context. That's how we use it, how we interact with it. We can use arenas and specific allocators to control behavior in our program, say you have access to only this much memory and so on. We could also say, hey, allocate a massive amount of memory, but we never allocate more, and just put it in an arena. You know, for example, if you are writing something that has very simple allocation patterns, you want to say, hey, you know, we use 2 gigs of memory. I'm going to just allocate that up front. And then we're going to pass it out to things in your program. And then we're going to just sort of never care, right? Absolutely. Go ahead, right? It's beautiful. Custom allocators are a boon to development. And so yeah, I hope this was useful. The next thing we're going to take a look at, I guess, yeah, we're going to try just sort of looking at some code from the standard library actually, and see, you know, what does it do, how does it do it, and we're going to get into sort of yeah, how does code in the wild actually look like. I'm also going to just do a brief video on how do we get Odin on our computer. What are some ways to do that, and some details about the platforms and so on. I use Linux, as you probably can see, but Odin actually runs extremely well on Windows. It is actually more popular on Windows. So don't worry about that. If you like Windows, you're in a good position here. And we might also take a look at some debugging in a video soon. But let me know what you want to see. And I'll take those things to heart, and have a good one. Ciao.